Lecture video for January 19th. Let's go ahead and get started, get those notes out, and I want you to add the product of powers rule to your notes. This rule states that if you have two exponents with the same base being multiplied, you can add their exponents. And I want you to get out your calculator and do a little test. So if you ever forget this rule, you can test it out by just using actual numbers and pick whatever numbers you want, but you could do something like 5 to the 4th times 5 to the 7th and see if that does equal 5 to the 11th by plugging in this side first, then plugging in this side and seeing if you get the same number. So, this would be really good on the SAT if you're unsure of a rule, is devise a quick test with your calculator, and then you'll know if you're remembering the rule correctly. Another one I want you to add to your notes is the power to a power rule. This one states that if I have an exponent being raised to a power, I can just multiply the powers and it'll be equivalent. And this works for a stack of exponents of any height. I could have x to the a to the b to the c to the d to the e, and then you collapse that stack. You have to keep the original exponent, but this could be x to the a, b, c, d, e, all being multiplied. Now parentheses are important. The parentheses have to be around the bottom part first and then continue like this on the way up. If you have any parentheses themselves, exponents in parentheses like that, then this rule doesn't work. That part of the stack wouldn't be able to collapse down like this. But as long as the parentheses are growing like this, then you're fine. Okay, so goal for today is to be able to rewrite radicals as exponents. Why the rules of exponents are much easier to work with, and we'll even get into a little bit of solving today. So what value makes sense for b in this equation? X to the value of b equals the square root of x. Can we come up with a number here so we can use an exponent instead of the square root symbol? Now I've already taught you what this number is, but let's prove it using our powers of exponents. Let's take both sides here and square them. On the left-hand side, I could collapse that stack of exponents and just make this x to the 2b. And on the right-hand side, the squared and the square root can cancel out. But I should leave something behind, so I'll leave a 1 in the exponent spot. Now, x to the 2b equals x to the 1. I can cross out the x's on both sides and just say 2b must be equal to 1. For this to be equivalent, then the exponents must be equivalent. Divide both sides by 2, and I get b equals 1/2. So it is valid to say that x to the 1/2 equals the square root of x. So instead of taking a square root, you can raise something to the power of 1/2. All right, and so this is a little bit strange to raise something to the power of 1/2. It really is just a consequence of us wanting our other rules of exponents to work for all values, that we can say something like this is true. Because raising something to the 1/2, it's like asking the question, multiply something by itself a half of a time. Well, that question itself doesn't really make sense, but to keep the rules of algebra consistent here, we can say multiplying something by itself a half of a time is the same as taking its square root. All right, so using that, can we simplify 216 to the 1/3? Well, if a square root of x is the same as x to the 1/2, then it follows that the cubed root of x is equal to x to the 1/3, and so on. Fourth root would be x to the 1/4. So this can be rewritten as the cubed root of 216. Well, 216 is a perfect cube. 216 could be rewritten as 6 cubed. And now the cubed root can cancel out, and I'm left with just a 6. All right, now what about something like 7 to the 1/2? Well, this could be rewritten as the square root of 7, but I want to make this very clear that neither of these is considered to be more simplified. These are equally simplified. So in a multiple choice test, you have to be comfortable going between these two forms, because even if it says simplify, it might give it to you with an exponent, it might give it to you with the square root. Neither is preferred. It's more about what you're going to do next with the number. All right, now what if we have something, a fractional exponent, but the number on top isn't a 1? Well, an idea for this is break this apart and make it x to the 1/7 times x to the 1/7 times x to the 1/7. We know we can break this apart because of that very first rule of exponents, saying that when we multiply the exponents with the same base, you add the exponents. Well, 1/7 plus 1/7 plus 1/7 is 3/7. All right, this would be the same as x to the 1/7 to the 3rd. Now x to the 1/7 is the same as the 7th root of x to the 3rd. And something we're allowed to do with radicals is bring exponents underneath the radical and then take them back out. So this is equivalent to saying the 7th root of x cubed. And this is another situation where neither of these is more simplified. All three of these are kind of equally simplified expressions of the same value. All right, the rational exponents rule. So this is what we just kind of discovered there, that the nth root of x to the m, the same as the nth root of x to the m outside the parentheses, or x to the m over n. And the trick to getting these in the right order is to not write your index like this, but write it really low down on the radical, and then your exponent real high so that there's a clear difference in height. And then the m and the n, they keep their relative orientation, m being higher than the n. So there's your trick to keeping this fraction straight. All right, can we rewrite this in exponential form? Square root of a to the 5th. Well, the index must be a 2. Then we'll just apply that rule we learned to rewrite this as a to the 5/2. All right, imagine that 2 very low down there and that 5 very high up here, and that's why we get something like this. And we're done. All right, let's use that rule to simplify this. So 27 to the 4/3. What would happen if you took 27 and multiplied it by itself 4/3 of a time? Well, to keep the other rules of math consistent, this does have a numerical value that, that question doesn't seem super sensical. This could be rewritten. Let's turn that 4/3 and write it the vertical fraction like that. I think that'll help us write this radical correctly. 27 to the 4th. Put that 4 up high, 3 down low. Now that 4 can come out from underneath the cubed root of 27 to the 4th. And the reason I did that is because 27 is another perfect cube. 27 is 3 cubed. So this can now become 3 to the 4th, and then 3 to the 4th is 81. All right, and that definitely is more simplified to write it down as just an 81. So it's worth going through the motions of turning it into radical form, because radical form sometimes enables us to simplify things further. All right, negative exponent rule. So if I take x and raise to the power of -1, that's the same as doing 1 over x to the nth. And this is another one that doesn't make sense with the definition of exponents, but it keeps everything else consistent. It doesn't make sense to take a number and multiply it by itself a negative number of times, but it keeps the rest of math consistent if we do it like this. It keeps our graphs nice, continuous curves. So it does have a meaning to a problem like this. Take 216 and multiply it by itself a -1/3 of a time. Well, this has a value. This can be simplified because this could be rewritten as 1 over 216 to the 1/3, which I think we saw on a previous slide 216 to the 1/3 is the same as the cubed root of 216, which is 6. I want to double check that. Yeah, 216. And we're done. It's 1/6. All right, quotient rule for exponents. X to the m over x to the n is the same as x to the m minus n. So dividing exponents with the same base, you can subtract their powers. Okay, so let's put a bunch of those rules together and simplify this complex radical. First thing I want to do is, if I've got radicals, I'd rather deal with exponents because I know my rules of exponents a lot better than my rules of radicals. So turn any radical into an exponent using that rule. Now here that index is written way up high, but we have to remember that 4 should really be nestled way down here and that 3 should be up high. So easy to get this fraction backwards if we're not paying attention. And this would be x to the 2/8. All right, now we can subtract those exponents because we've got two exponents with the same base. So subtract their powers. So x to the 3/4 minus 2/8. All right, in order to subtract two fractions, you need a common denominator. So I'll turn that first fraction into a 6/8 minus 2/8. And now I can subtract them and I get 4/8, which can simplify, divide the top and bottom by 4, and we get x to the 1/2, which is equivalent to the square root of x, but again, it just depends on what we're going to do next, whether we want to keep it in exponential form or put it back into radical form. I would say if we started with radicals, we're probably going to want to end with radicals, but you never know, so be able to go back and forth. These are equally simplified. All right, now let's use some rules in solving. Here we go, x to the 3/2 minus 4 equals 60. Let's add 4 to both sides. I'm going to try to isolate that variable. X to the 3/2 equals 64. Now we can use the power to a power rule to get rid of this 3/2. Just raise both sides to the power of 2/3, the reciprocal of 3/2. Because when you multiply a number by its reciprocal, it becomes a 1. And now I would just have x by itself equals 64 to the 2/3. All right, and then this would be the same as the cubed root of 64 squared, but I'm just going to plug it as it is right there directly into my calculator. Should be able to handle that. So 64 to the power of, keep it in a set of parentheses, 2/3, so it all goes in the exponent, and I get 16. All right, power of 0 rule. So this rule is anything to the power of 0 equals 1. So that can be useful. All right, let's simplify this big one. Copy it down. All right, so first thing, I do see a power of 0. So this value right here is going to become a 1 and basically go away because 2 times 1 is just a 2. All right, v cubed times v cubed, I've got same base. This can become a v to the 6th. Let's just do those two steps in our first simplification right here. So 2 to the v squared over v to the 6th, all to the -3. All right, I want to keep working inside these parentheses. I've got exponents to the same base being divided, so I can subtract those exponents. This can become 2v to the 2 minus 6, all to the -3. All right, let's bring that up over here. That becomes 2v to the -4 to the -3. Now I want to bring that -3 inside. Now watch out, when we distribute exponents, they have to also be distributed to the coefficient. It's not like distributing something in front that's being multiplied. Exponents do go to the coefficient and the variable separately. So now I've got 2 to the -3rd times v to the, this is an exponent to an exponent, so I can just multiply them. It'd be v to the 12th. And now 2 to the negative third would be the same as 1 over 2 cubed v to the 12th. I'll bring that v to the 12th all the way to the top of this fraction and just make this v to the 12th over 8. And yeah, just know that there's often several ways to write these. I could have rewritten this as 1/8 v to the 12th. If you still have a fraction in the exponent, then you've got some options of how to write that. If you have a negative up here, you can rewrite it with the negative or rewrite it into the fraction. But here, it would be one of these two forms would be the most simplified. All right, and I'll bet a few more here. That's that for this lecture video. Have a good rest of your day.